Now, the next topic is residue. The screen is visible?
Yes, sir.
Right. Residue. In the previous class, we have learned about singularities, types of singularities. Okay, first one is removable singularity. Second one is pole of order 1 called as simple pole of order m. Next one, and the next one is essential singularity. And we did some problems to clear the concepts of singularities, types of singularities. After that, now the residue. This is very important. Using this residue, we can solve the real integrals and some complicated integrals, improper integrals. Okay. Without this, you cannot solve improper integrals. So listen carefully. Residue concept. The quotient of, Lorentz series expansion. Okay. We have Lorentz series expansion. Lorentz series expansion of f of z about the singularity z equal to a is, what is that? F of z equal to, do you remember positive power series? Okay, a2 into z minus a whole square and so on, plus negative power series z minus a whole power minus 1, a minus 2 z minus a whole power minus 2 and so on. Okay, right? This is Lorentz series expansion, and in terms of summation, one can write like this: an z minus a whole power n plus summation n equal to 1 to infinity a minus n z minus a whole power minus n. Okay, this is Lorentz series expansion of the function f of z. Okay, in this Lorentz series expansion, the coefficient of z minus a whole power minus 1, z minus a whole power minus 1, that is a minus 1, that is a minus 1 is called residue, residue of f of z, okay, at z equal to a, residue of f of z at z equal to a. Okay, that is, therefore, what is the formula for a minus 1? We have a minus n formula is what in Lorentz series expansion? A minus n formula, do you remember? A minus n equal to 1 by 2 pi I integral f of z by z minus a whole power minus n plus 1 dz. Do you remember? Right? A minus n, we have written the formula. Therefore, what is a minus 1? Therefore, put n equal to 1 by 2 pi I integral over c f of z by, what is this becomes? If I put n equal to 1 whole power 0 dz. Done? So that is implies a minus 1. What is the formula of a minus 1? 1 by 2 pi I integral over c just f of z dz. Okay, this is f of z dz. What is a minus 1? I called a minus 1 as residue. Therefore, residue of f of z, this is the notation how to write residue of f of z at z equal to a is a minus 1. And what is that formula? 1 by 2 pi I integral over c f of z dz. This is the residue formula. So to find the residue of any function f of z, What we have to find? First, we have to find Lorentz series expansion. In that Lorentz series expansion, get a minus 1. That is nothing but coefficient of z minus a whole power minus 1. Z minus a whole power minus 1. Hence, see what this becomes. Hence, from the above, that means from the residue formula, from the above, we have, hence, from the above, we have, from the above, we have, what is this one? Integral value is what? Integral over C, f of z dz is equal to, just give me a minute, just a minute. Hence, from the above, we have, what is this integral value? Integral over C, f of z dz value. Take this 2 pi I this side. 2 pi I into a minus 1. 2 pi I into a minus 1. Therefore, integral over C, f of z dz value is what? 2 pi I into residue of f of z at a. This is another formula. That means if I want to evaluate integral of f of z dz, already we know how to evaluate this integral. Integral of f of z dz value, first by using Cauchy's theorem. If f of z is analytic in entire region, then this value equal to 0. Right? Next one, if it is not analytic, then we go for Cauchy integral formula. We go for Cauchy integral formula. Right? And the next one is what? That is evaluation. And the third concept is evaluation of this complex integral by using residue theorem. By using residue theorem, 2 pi I into residue of f of z at z equal to a. And what is it here? Only one singularity is here. What is that singularity? A. What is that singularity? A. Okay, remember this. Now, the next one is residue theorem. Residue theorem. The function may possess many singularities, maybe poles or essential singularity like that. See, what is residue theorem? Using this residue theorem, we can evaluate this complex integral. This complex integral over C f of z dz. And what is the statement? See, if f of z is analytic, if f of z is analytic in a closed curve C, in a closed curve C, what is this? F of z is analytic in a closed curve C, in a closed curve, not like that, don't say in a closed curve, it's given mistake. F of z is analytic in a region bounded by closed curve C, bounded by closed curve C, okay, except at a finite number of singular points, particularly poles, at a finite number of singular points, in brackets, compulsory these are poles within C, then integral over C f of z dz, integral over C f of z dz equal to 2 pi I into, see this one, sum of the residues at the poles, sum of the residues at the poles or singular points at the poles within C. Okay, just I'm giving idea. For example, this is one closed curve C. F of z, what is the given statement? F of z is analytic in a region. F of z is analytic in this region except at a finite number of singular points. What I'm taking, A1, A2, some A3 and so on, AN, this point. At these points at A1, A2, A3, which lies inside C, the function f of z is not analytic. Got this point? Right? Analytic everywhere except at this finite number of singular points. Then what we have, f of z dz, what is the value of this integral? 2 pi I into, for example, see, if it is only one singularity is there, then what is the formula? 2 pi I into the residue value. Now how many singularities are here? N singularities are there. So 2 pi I into, what is this formula? Sum of the residues. F of residue at A1 plus residue at A2, and so on. What is this? Residue of f of z at AN. So what is the principal residue theorem? If f of z is analytic, and except at a finite number of singular points which lies inside the curve, then integral f of z dz is nothing but 2 pi I into sum of the residues at the singularities which lies inside. This is the residue theorem. Statement is also important. Now, how to find residue without finding the Lorentz series expansion? That is the next topic. Residue formula, you know, a minus 1 coefficient of z minus a whole power minus 1. Next one, integral f of z dz value is what? If one singularity is there, 2 pi I into residue at a. If more number of singular points are there, then we have to apply residue theorem. What it states that f of z is analytic in a region bounded by closed curve C except at a finite number of singularities which lies inside C, then integral value f of z dz is nothing but 2 pi I into sum of the residues at the singular points or poles which lies inside. Now, one by one formulae to find residue. First one, if f of z has a simple pole, you know what is meant by simple pole? What is that? Pole of order 1 at z equal to a. Only one pole, simple pole is there. Then what is the residue formula? Residue of f of z at a is nothing but limit z tends to a, z minus a into f of z. All of you have to remember this formula. These are very useful. Just what is the hint? Just briefly I will give hint. What is the hint here? Lorentz series of f of z at z equal to a, the simple pole at z equal to a. I will write simple pole. Z equal to a is a simple pole. Simple pole means what? Pole of order 1 is. Pole of order 1 means what? Do you remember? Pole of order 1 means f of z equal to a naught, positive powers. Pole of order 1 means what? Up to z minus a whole power minus 1 term only. Pole of order m means what? Negative powers are m terms. That means up to what terms negative powers? A minus m, z minus a whole power minus m. Now since this is a simple pole, expansion is up to this one only. So what I have to do? Let us multiply on both sides by f of z, z minus a. Multiply by z minus a. Then what is this becomes? A naught into z minus a, a1 into z minus a whole square, and so on, a minus 1. Then I need what is my residue? Exactly a minus 1. Therefore, to get a minus 1, I am applying limit z tends to a, z minus a into f of z. Limit z tends to a means 0 plus everything goes to 0 except to my a minus 1. Therefore, what is a minus 1 is nothing but limit z tends to a, z minus a into f of z. What is a minus 1 is nothing but residue. Therefore residue of f of z at simple pole is, what is the formula? Z tends to a, z minus a into f of z. This is simple pole formula, right? There is another formula for simple pole. Second one, residue of f of z at simple pole. Simple pole means pole of order 1. Remember, simple pole. Another formula. This is, you say, another formula. But this formula is applicable in some cases only. If f of z can be written as, this is the thing, can be written as, how to write f of z? F of z equal to some phi of z by psi of z. F of z can be written as phi of z by psi of z, such that what is this thing? If I put simple pole z equal to a, if I put a value in the numerator, it should not be 0. It should not be 0. And if I substitute a value in the denominator, then, and what is psi of z? Psi of z must be of what structure? Z minus a into some another function. You take some another function, some capital F of z. That means if I put a value in psi of z, what is this becomes? 0. What is this becomes? 0. So psi of z must be what structure? Simple pole, z minus a into some another function. Then residue of f of z at a, is phi of a by psi dash a. Phi of a by psi dash a. This is another formula. I'm not giving the proof of this one. You can do yourself. It is given in the textbook. Okay, phi of a by psi dash a. And a third formula, and a third case, if this is important, if f of z has a pole of order m, say z equal to a is a pole of order m. Pole of order m means what? In the Lorentz series expansion, how many negative terms will be there? M negative terms. That means series end term is what? A minus m into z minus a whole power minus m. Z minus a whole power minus m. Then see the residue formula. Residue of f of z at a, pole of order m. This is, the formula is 1 by m minus 1 factorial, d m minus 1th derivative, of what? Z minus a whole power m into f of z. Z minus a whole power m into f of z. And this entire should be evaluated at z equal to a. Let me give hint for this one. Then since z equal to a is a pole of order m, the Lorentz series, LS I will write, the Lorentz series of f of z about z equal to a is what is the formula? F of z equal to a naught positive power series z minus a plus a2 z minus a whole square and so on, negative power series a minus 1 z minus a whole power minus 1, a minus 2 z power a whole power minus 2 and so on, a minus m z minus a whole power minus m, z minus a whole power minus m, since it is pole of order m. So what is the thing? I have to get what term? What is my residue formula? Always remember, residue is nothing but coefficient of a minus 1, the coefficient of z minus a whole power minus 1, that is a minus m, a minus 1. So let me multiply on both sides by z minus a whole power m, a naught into z minus a whole power m, a1 into z minus a whole power m plus 1 and so on, positive powers. Coming to negative power, what is this becomes? Z minus a multiplied by m means m minus 1, done. A minus 2, z minus a whole power, what is this? M minus 2 and so on. What is the last term will be? A minus m, a minus m. Now I need what? I need what? A minus, yeah, a minus 1 is required. A minus 1 only required. That means I have to make this one as 1. I have to make this one as 1. Now, so to get this as 1 as a constant or constant, differentiating on both sides, m minus 1 times with respect to z, m minus 1 times with respect to z. Then what happened? D m minus 1 or derivative of z minus a whole power m f of z by dz whole power m minus 1, this is in one bracket, okay, equal to, what is this first one? See, I'm taking how many times differentiation? M minus 1 times differentiation, m minus 1 times differentiation. Then what is this becomes? What is this becomes? There will be one z minus a will be there, definitely. See, just roughly, z minus a whole square is there, m value 2 here. Then m minus 1 times derivative means 1 time derivative 2 into z minus a will be there. So same logic, a naught into m into m minus 1 into and so on. This is the first term. There will be one first term. And m plus 1 will be there. M plus 1 means what? A1 into m plus 1 into m minus 1 into dash. There will be whole square will be there and so on. Coming to a minus 1, what is this becomes? Plus a minus 1, z minus a whole power m minus 1 derivative with respect to z, m minus 1 times is what? M minus 1 factorial. And coming to next one, this is m minus 2, this is, I'm taking how many derivatives? M minus 2, m minus 1 derivatives. So all these terms goes to 0. All these terms goes to 0. Now you apply limit. Now you apply limit on both sides. What is for this? Z minus a whole power m into f of z. Z tends to a means what? This part 0, this part 0, first term, second term, all positive power 0, except what? A minus 1. Everything will be 0. That implies what is a minus 1 value? 1 by m minus 1 factorial, limit z tends to a of what? M minus 1th derivative of what? Z minus a whole power m into f of z. So limit z tends to a, I have written in the formula as at z equal to a. See, at z equal to a. Okay, both are same. Now this is the residue formula. This is the residue formula. Residue of f of z at a, where what is a? Pole of order m. Pole of order m. Okay, this is the formula. Any doubts in these three cases? Reply. Any doubts? If any doubts, I will explain again. Any doubts? Yes, anyone reply?
No, sir.
Okay, I'm
No,
going to
sir.
process now. Yeah. Find the residue. Find the residues at the singular points of f of z, where, first question, f of z equal to z by z plus 1 into z minus 2. Second question, f of z equal to z square by z square minus 2z plus 2. Z square minus 2z plus 2. Solution. First one, f of z equal to z by z plus 1 z minus 2. Z plus 1 z minus 2. Clearly, f of z is not analytic. Not analytic at z equal to what points? Minus 1 and z equal to 2, which are, see, which are simple poles. I told you already how to identify simple pole. There is no squares here. There is no squares, cubes. Therefore, pole of order 1. Simple pole means pole of order 1. Okay. And I have given formula also. How to check pole of order 1, like that. So I have to, simple pole formula I have to apply. Therefore, the residue at a simple pole z equal to a is given by, what is the formula? Simple pole z equal to limit z tends to a, z minus a into the function. Okay. Therefore, residue of f of z at, what is first one? Minus 1. Limit z tends to minus 1, z minus of minus 1 into f of z. So limit z tends to minus 1, z plus 1 into, what is this? F of z, z by z plus 1 into z minus 2. So these two gets cancelled. So, and substitute this z equal to minus 1. So 1 by 3. So 1 by 3 is the residue. Next one, residue of f of z at 2. Residue of f of z at 2. So formula is what? Limit z tends to 2, z minus 2 into f of z. So limit z tends to 2, z minus 2 into z by z plus 1 into z minus 2. These two gets cancelled, and substituting the limit 2 by 3. 2 by 3. Got it? Okay. This is one way of doing. Okay. And the next one, what is the next problem? Second problem. F of z equal to z square by z square minus 2z plus 2. F of z has singularities or not analytic? F of z is not analytic at denominator equal to 0, right? Now what are the roots for this? I have to find the roots. So z equal to minus b plus or minus b square minus 4ac by 2a. So 2 plus or minus, this is minus 4. That is 2i by 2. So what are the poles here? Z equal to 1 plus or minus I. That is z equal to 1 plus I, 1 minus I are the, not repeated now, are the simple poles. Simple poles, right? Therefore, what is the residue formula? First one, residue of f of z at 1 plus I is limit z tends to 1 plus I, z minus of 1 plus I into f of z. Okay, that is equal to limit z tends to 1 plus I, z minus 1 plus I into f of z is what? Z square by z square minus 2z plus 2. That is limit z tends to 1 plus I, z minus 1 plus I. And what are the, what are the roots of this? Two roots are there. What are the roots? One is z minus 1 plus I is the one root, and another one is what? 1 minus I. So I can factorize this like this. Done. So these two gets cancelled. That is equal to, now apply limit 1 plus I whole square by 1 plus I minus 1 plus I minus 1 plus I. So this is 1 minus 1 plus 2I whole by, and 1 gets cancelled, 2I, 1 gets cancelled. So this residue is 1. Now another pole, simple pole, residue of f of z at 1 minus I, that is limit z tends to 1 minus I, z minus 1 minus I into f of z. Okay, I will write one more step. That is equal to limit z tends to 1 minus I, z minus 1 minus I f of z, z square by, what are the factors? One is 1 plus I, another one is 1 minus I. So these two gets cancelled. Apply the limit 1 minus I whole square, 1 minus I minus 1 minus I. So 1 minus 1 minus 2I by 1 gets cancelled, minus 2I. This is also 1. This is also 1. Done. This is one problem. And the next one, let me take pole of order 2 like that. Okay, next problem. Find the residue of f of z equal to 1 plus z plus z square by z minus 1 whole square into z plus 2. Solution. F of z is not analytic. Not analytic at what point? Z minus 1 whole square into z plus 2 equal to 0. That implies z equal to 1 comma 1 comma 2. 1 is repeated 2 times. Therefore, z equal to 1.
Z equals to minus 2, sir.
Yeah, minus 2. Z equal to 1 is a pole, since it is repeated 2 times, pole of order 2. And z equal to negative 2 is a pole of order 1. That is simple pole. This is simple pole. Okay, now residue. Therefore, residue of f of z at what point? 1. What is the formula? So say here m equal to 2. Pole of order m equal to 2. What is the formula? I will write here. Residue at a pole of order m is, I will write a here, general formula I am giving. What is that formula? 1 by m minus 1 factorial, limit z tends to a, m minus 1th derivative of what? Z minus a whole power m into f of z. This is the formula. Now what is the m equal to here? M equal to 2. M equal to 2 for z equal to what? 1. Therefore, what is this residue formula? Becomes 1 by 1 factorial, limit z tends to a, d by dz of what? Z minus 1 whole square into f of z. Z minus 1 whole square into f of z. So limit z tends to a. Derivative is there. Okay. D by dz of z minus a whole square, and what is f of z? 1 plus z plus z square by This is 1. Z minus 1 whole square into Z plus 2. So now these two gets cancelled. For the remaining part, I have to find derivative. That is, limit Z tends to A, d by dz of what? 1 plus Z square by Z plus 2, u by v method. So limit Z tends to A, Z plus 2 into 1 plus 2Z minus 1 plus Z square into 1 whole by Z plus 2 whole square. Now just apply the limit, no need to simplify. Z tends to 1, all of you. This is 1. Now 1 means what? This is 3. This is 3. 1, 1, 1. This is also 3 by 3 square. So 9 minus 3, 6 by 9. That is 2 by 3 is the residue. 2 by 3 is the residue. Next one. Z equal to minus 2 is a simple pole. Is a simple pole. Therefore, the residue of f of z at minus 2. Residue of f of z at minus 2. Simple pole formula you know now. Z tends to A value is minus 2 into f of z. Simple pole formula. Limit z tends to minus 2. So this is z plus 2. 1 plus z square whole by z minus 1 whole square into z plus 2. These two gets cancelled and minus 2 you substitute. 1 minus 2 plus 4 by minus 2. This is 9. That is 5. 5 minus 2, 3 by 9. That is 1 by 3 is the answer. 1 by 3 is the answer. Okay, this is one problem. Next one. Find the residue. Find the residue at all the singular points. At all the singular points of f of z. First question. F of z equal to cot z. Second question. F of z equal to secant z. F of z equal to cot z. F of z equal to secant z. Solution. First one. F of z equal to cot z. Cot z can be written as what? Cos by cosine by sine. Done. Now what are the singular points here clearly? What are the singular points? Yes. F of z has singular points or not analytic. Singular points. Sin z equal to 0. That is z equal to what? N pi. Right? Z equal to n pi. N belongs to z. N belongs to z. These are the singular points. These are the singular points. And any singular point is repeated? No. And z equal to and z equal to n pi are the how many? Infinitely many are the simple poles. Or what poles? Simple poles. Not repeated. These are not repeated or the simple poles. Now I have to see the structure of this cot z is cosine z by sin z. It is what is the form? Phi of z by psi of z form, isn't it? Phi of z by psi of z form. Here I will write like this: cot z f of z equal to cot z equal to cosine z by sin z is equal to phi of z by psi of z. And when we have to apply this formula, the conditions are such that phi of a not equal to 0. That implies phi of n pi. What is that? Cos n pi not equal to 0. Condition satisfied. Coming to psi of z. Psi of z is what? Sin z. And what is psi of a? Must be 0. That means psi of a must be 0. Right? So I can write this is sin n pi equal to 0. Sin n pi equal to 0. You write n pi here. So conditions, those two conditions are satisfied. Therefore, residue of f of z at n pi, all the residues, all the poles. What is the formula? Limit n tends, no, not this. I will write the formula first. At a equal to, what is the formula? Phi of a by psi dash a. Phi of a by psi dash a. Nothing but one can write phi of z by psi dash z at z equal to a. You can write like this also. Therefore, residue of f of z at n pi is nothing but what is this? Cos z by d by dz of sin z. This entire at z equal to n pi. So this is cos z by, what is derivative of sin z? Cos z at z equal to n pi. Anyway, this is 1. Anyway, this is 1 for all n pi. For all, therefore, residue of f of z at n pi is 1 for all n. For all n. Got it? Right? And the next one. F of z equal to, what is that function? Secant z. Therefore, f of z equal to secant z means what? 1 by cosine z. 1 by cosine z. And here, f of z has singularities. Singularities at cos z equal to 0. Cos z equal to 0 means what? Z equal to odd pi by 2. Do you remember, right? 2n plus 1 pi by 2. 2n plus 1 pi by 2. N belongs to z. N belongs to z. Done? And this f of z equal to 1 by cosine z is what form? Phi of z by psi of z, where phi of z is taken as 1 and psi of z obviously cosine z. Cosine z. Clearly, phi of a. Phi of a means what? Phi of 2n plus 1 pi by 2. What is this value? 1. Not equal to 0. And the psi of a means what? Psi of 2n plus 1 pi by 2. That is nothing but cosine 2n plus 1 pi by 2. Definitely this is 0. So conditions are satisfied. Therefore, and z equal to 2n plus 1 pi by 2. These are not repeated. N belongs to z are simple poles. Are simple poles. Okay, these are not repeated. Therefore, residue of f of z at what point singular poles? 2n plus 1 pi by 2 is nothing but, what is this? Phi of a by psi dash a. Phi of a by psi dash a. That is nothing but phi of a is 1. Psi dash a means what? D by dz of cosine z. This entire at z equal to a. A value is what? 2n plus 1 pi by 2. So what is this value? This is equal to 1 by minus sin z. At z equal to 2n plus 1 pi by 2. 2n plus 1 pi by 2. So what is this value now? This is minus 1 by sine 2n plus 1 pi by 2. That means sine odd pi by 2. Sine odd pi by 2. For example, if I take sine pi by 2, 1. If I take sine minus pi by 2, negative 1. Negative 1. So when n equal to minus 1, negative. When n equal to plus, when n equal to 0, okay. So what is this? I can write. Anyone? How to write? Okay, let me write clearly. Let me explain. At side, when n equal to 0, what is this value? What is this value? Residue.
Sir, for even positive,
yeah,
for
just
odd negative, sir.
Yeah. When n equal to 0, what is this value? Sine pi by 2, right? Minus 1 by sine pi by 2. That is negative 1. When n equal to plus or minus 1, what is the residue? Minus 1 by, when n equal to plus 1 sine 3 pi by 2. Is it correct? Sine 3 pi by 2 means negative. When n equal to minus 1, when n equal to minus 1 minus pi by 2, so minus 1 gets cancelled, 1. Done. When n equal to plus or minus 2, then what is the residue? Minus 1 by sine 5 pi by 2 plus or minus 5 pi by 2. One is when n equal to 2, 5 pi by 2 positive, so negative 1. And this is when n equal to minus 2 minus 3 pi by 2. Yeah, correct. So when I can write this is n equal to 0 when n is even, negative 1. When n is even, negative. When n is odd, positive. Means I should write plus 1. Yeah, now it is right. This is the residue formula. Minus 1 whole power n plus 1. Minus 1 whole power n plus 1. Next one. There are many problems are there. Anyway. Let me tell you. Pole of order, that's okay, no problem. Yeah, take this one problem. Find the residue of f of z equal to 1 by z cube plus z power 5. So f of z equal to 1 by z cube plus z power 5. So what is the common I can take? Z cube common, 1 plus z square. Therefore, f of z has singularities at z equal to 0 and z equal to and z square plus 1 equal to 0. That implies z equal to plus or minus I. Clearly, see, z cube is here. Clearly, z equal to 0 is a pole of order 3. Pole of order 3. And z equal to plus I minus I are the simple poles, not repeated. These are the simple poles. I think you can calculate now. Okay. Residue of f of z at 0. What is this? Is 0 is a pole of order 3. So what is the formula? 1 by 3 minus 1 factorial. Limit z tends to 0. Z d 3 minus 1 means double derivative of what? Z minus 0 whole power m into f of z. This is the formula. So 1 by 2 factorial. Limit z tends to 0. Double derivative of what? Z cube into what is the function? 1 by z cube into 1 plus z square. So z cube gets cancelled. 1 by 2 factorial. Limit z tends to 0. D by dz of one derivative is what? Minus 1 by 1 plus z square into 2z. Right? This is over. And one more derivative I have to calculate. 1 by 2 factorial. Limit z tends to 0. I will take minus outside. 2z. So 1 plus z square into 2 minus 2z into 1 plus z square derivative 2z whole by 1 plus z square whole square. If any corrections, suggest me. So minus 1 by 2, substitute z equal to 0. What is this value? This is 2 now. Okay. So not 0. 1 plus 0 into 2 minus this value 0 minus this value 0 and this is 1. So this is equal to just 2 minus 1. Is it correct?
So check first derivative, sir.
Mistake, huh? Minus I have taken outside. 1 plus z square into 2 minus 2z into 2z. Correct. Correct only. minus 1 by 2, this is 2 only, this is 0, and this is 0 substituted 1, 2 by 2, 1. Yeah, correct. This is the residue. Next, now residue of f of z at I, simple pole. I is the simple pole, so z tends to I, z minus I into f of z. So limit z tends to I, z minus I into 1 by z cube into z square plus 1. So I can write this one as limit z tends to I, z minus I into 1 by z cube. I will write z minus I into z plus I. So z minus I gets cancelled. For the remaining part, apply limit 1 by, this is I cube and this is 2I. So 1 by 2 I power 4. So 1 by 2. 1 by 2. Another one. Next one. Residue of f of z at minus I. Limit z tends to minus I, z minus of minus I into f of z. So limit z tends to minus I, z plus I into, I will write directly the factorization, z plus I into z minus I. So now these two gets cancelled. So this is 1 by minus I whole cube minus 2I. So 1 by 2I power 4. So 1 by 2. These are the residues. Okay. Next one. Check this.
Sir, minus 1 by 2.
Minus 1 by 2. Why? Sure. Z plus I gets cancelled. Minus I cube. So minus 1 whole cube. See, minus 1 whole cube negative. I cube into I power 4. Minus 1 whole cube into minus 1 whole power 1 positive. Correct only. Still any doubt? Yes?
Sir, for residue of 0 only, sir. First derivative, we should get 1 plus z square whole square.
Where?
Residue of 0. 0. First derivative, sir. Power we should get 2 na, sir. 1 plus z
This is
square
whole
whole
square.
square.
This is whole square. Correct? Right.
Yes,
This
sir.
is whole square. Above. Then it is gone. Limit z tends to 0. 1 plus z square whole square. So there is a mistake here. So 2z as it is. This is what? 2 into 1 plus z square into 2z. Correct? And z tends, no problem. When z equal to 0, this entire term will be 0. It is right only. This is about residue, calculation of residues. Now, see, next problem. Evaluate. Integral over C. Sin z by z into cos z. dz, where C is mod z equal to 2. Where C is mod z equal to 2. Okay. Solution. Now, whenever integration is given, integral f of z dz is given, first to go for Cauchy's theorem. Always. That is standard one, Cauchy's theorem. And what is my circle is given as mod z equal to 2. That is 2. This is 2. Minus 2. Minus 2. Okay. And this is my function sin z by z into cos z. What are the singular points here clearly? One is z equal to 0. Where is z equal to 0? Inside. That's enough. Whenever inside there is a singularity, Cauchy's theorem fails. Not applicable. Done. One point is over. Next one, I have to apply Cauchy integral formula. To apply Cauchy integral formula, the function integrand must be of this structure. Do you remember? F of z by z minus a only. F of z by z minus a only. But this integrand is not that form. So, not possible. So, definitely another technique is what? Now, evaluation of integral by using residue theorem. So, I am applying residue theorem now. F of z equal to sin z by z into cosine z. Sin z by z into cosine z. Okay. The singularities are The singularities are, what are the singularities? Z equal to 0 and cosine Z equal to 0. That implies Z equal to 0. And what does cos Z equal to 0 means what? Plus or minus pi by 2, plus or minus 3 pi by 2, and so on. And so on, odd 2n plus 1 pi by 2, like previous case, right? And now I am listing. And among these singular points, among these, all these are, let me write. What are these? All these singular points. All these singular points are not repeated now. All these singular points are simple poles. Simple poles, not repeated. And among these poles, now which lies inside? Which lies inside? Tell me, among these poles, Z equal to 0 lies inside, plus or minus pi by 2. Plus or minus pi by 2 means what? 3.14 by 2. 1 point something. 1 point something means lies inside. This somewhere plus pi by 2 is here, somewhere minus pi by 2 is here. And coming to 3 pi by 2 is what? 3 into 3.14. Okay, just I'm giving here a idea. 3.14 by 2. Okay. Next one is 3 into 3, 9 point something by 2 means what? 4 point something. Those are outside or lie inside. Or lie inside mod Z equal to 2. That means, see, what is the residue theorem? States that integral over C f of Z dz equal to 2 pi I into sum of the residues at the poles lies inside C. So which poles lies inside now? 0 and plus or minus pi by 2. 3 poles are lies inside. Therefore, lies inside C. Therefore, by residue theorem. We have integral over C f of Z dz is equal to what? 2 pi I into sum of residues what happened? Sum of residues lie, just wait, sum of residues lie inside C. Sum of residues at poles lie inside C. Okay, this is the formula. Now, first one, let us find residue. Therefore, residue of f of Z at 0. Simple pole formula I have to apply. Limit Z tends to 0 into f of Z. That is equal to limit Z tends to 0. Z into what is f of Z? Sin Z by Z into cosine Z. So Z gets cancelled. Z tends to 0. If I substitute 0 by 1, first one is 0. Next one. Residue of f of Z at pi by 2. Limit Z tends to pi by 2. Z minus pi by 2 into sin Z by Z into cosine Z. Z into cosine Z. This is the formula, right? If I apply this formula, it is not possible to cancel this Z minus pi by 2, right? It is not possible to cancel Z, like Z cancel in every problem. This term, this whatever Z minus A term will get cancelled when I factorize this f of Z. Now it is not possible. Or what I can apply formulas, another formula for simple pole. Z tends to pi by 2, phi of Z by psi dash Z, where phi of Z is what? Sin Z. Psi of Z is what? Psi of Z is what? Z into cosine Z. Z into cosine Z. Done? Therefore, what is this formula? Now limit Z tends to pi by 2. Nothing but at Z equal to pi by 2. Remember, sin Z. And what is the derivative of psi of Z? UV formula. UV formula minus Z into cosine Z derivative minus sin Z. Now you apply 1. This is 0. This is pi by 2, 1. So what is this value? Minus 2 by pi. residue of f of z at pi by 2. Now, residue of f of z at minus pi by 2. Limit z tends to minus pi by 2, phi of z by psi dash z. So already I have calculated that. So I can substitute directly. This is sine z by cosine z minus z into sine z. So this is negative 1 by 0 minus pi by 2 into minus 1. Is it correct? Right. So negative, 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 negative. So 2 by pi. I'm getting 2 by pi. This is residue of f of z at minus pi by 2. Therefore, by residue theorem, we have integral over c f of z dz is equal to 2 pi I into sum of residues at poles lies inside plus residue of f of z at pi by 2 plus residue of f of z at minus pi by 2. At minus pi by 2. So 2 pi I into, what is the first one? I think 0. What is the second one? Minus 2 by pi. And the third one, 2 by pi. What is the answer?
0.
0. This is 0. Right? This is one model. Next one. Yeah, you check this. I'm giving some problems for you, assignment in between. Which problem? Yeah. Find residue of f of z equal to z square by z square plus 1 whole square. Z square by z square plus 1 whole square. Next one, find the residue of f of z equal to z into sine 1 by z. Next, find the residue of f of z equal to z into cosine 1 by z. Cosine 1 by z. Yeah, those are simple enough. Yeah, take this. F of z equal to 1 minus e to the power of 2z by z power 4. F of z equal to cot z. I think already we did this one. Okay, no problem. Yeah, you try this. See, in this problem I will tell this or this problem how to find f of z equal to, what is this problem? Z into sine 1 by z. What happened? Z into sine 1 by z. Right? Now to find singular points, is there any possibility? Yes. Sine range is what? Between minus 1 to plus 1. Okay, between minus 1 to plus 1. If I put z equal to 0, I'm getting sine infinity. Definitely it lies between minus 1 to plus 1 only. So in such type of problems, when there is an ambiguity to check what is the singularity, then use the expansion. Use the expansion, sin x expansion. What is that? X minus x cube by 3 factorial plus x power 5 by 5 factorial and so on. And so on. Simple technique this is. If there is a, this is one. If there is a series expansion is available, you better apply that. So take z inside. This is 1 minus 1 by 6 into z square plus 1 by 5 factorial into z power 4 and so on. And done. So on. Done. This is f of z expansion. Since residue is the, what is this one? Is the Lorentz series expansion. Is the Lorentz series. is the Lorentz series expansion about what singularity? Z equal to 0. About Z equal to 0. Therefore, residue is the coefficient of Z minus A whole power minus 1. That is 1 by Z minus A. That is A minus 1. Here, what is A value? 0. Okay. Since in the expansion, in the above expansion, there is no 1 by Z term, right? Clearly, what are the terms here? Z square, Z power 4, all those are there, negative powers. There is no 1 by Z term, hence A minus 1 is 0. Therefore, residue of f of Z at 0 is 0. There is no residue here, right? Okay. And similarly, if you apply the another one, what is that? F of Z equal to Z into, maybe let me check whether I will get here or not. Z into, what is the cosine Z expansion? 1 minus x square by 2 factorial plus x power 4 by 4 factorial, like this. So take Z inside, 1 by 2Z will be there. Yes, now you will get here Z cube and so on, right? Is the Lorentz series expansion. Positive power is there and negative power is also there. Lorentz series about what singularity? Singularity is what? Clearly Z equal to 0. Z equal to 0. Therefore, residue of f of Z at 0 is coefficient of 1 by Z. That is what? That is A minus 1. That is minus 1 by 2. 1 by Z quotient is what? Minus 1 by 2. This is another problem. Now, next problem. Evaluate integral over C Z minus 3 by Z square plus 2Z plus 5 dz, where C is the circle. I will tell one problem in these cases. A, mod Z equal to 1. B, mod Z plus 1 minus I equal to 2. C, mod Z plus 1 plus I equal to 2. I will tell any B or C problem. What is f of Z here? Z minus 3 by Z square plus 2Z plus 5. Z minus 3 by Z square plus 2Z plus 5. The singularities are Z square plus 2Z plus 5 equal to 0. So what is Z equal to? Minus 2 plus or minus 4 minus 20 by 2. So Z equal to, what the singularity is? Z equal to minus 16. So 4, 2i. Minus 1 plus or minus 2i are the singularities. Are they not repeated now? Are they simple poles? Are they simple poles? Not repeated, therefore these are the simple poles. Now what is, I am taking the problem B. I am considering B. C is the circle. Remaining problems assignment. C is the circle. What is that? Mod Z plus 1 minus I equal to 2. Now I will write, let us check whether which pole lies inside. At Z equal to minus 1 plus 2i, mod Z plus 1 minus I equal to minus 1 plus 2i plus 1 minus I. What is this? 2i minus 1 mod I, that is 1 less than 2 radius, less than this radius. Remember, radius is 2, less than 2. Is it correct? Minus 1 plus 1 gets cancelled, right? Therefore, Z equal to minus 1 plus 2i lie inside C. Now at Z equal to what is another pole? -1 minus 2i mod Z plus 1 minus I is equal to -1 minus 2i plus 1 minus I mod minus 3i, that is 3. It is greater than radius, greater than 2 radius. Therefore Z equal to -1 minus 2i lie outside C. But what we required only the poles lies inside C. Poles lies inside C only, not outside, Therefore let us find residue. Residue of f of z at what pole? -1 plus 2i. Simple pole, that is simple pole. So -1 plus 2i z -1 plus 2i into f of z. A value -1 plus 2i. I'm writing clearly every part. Z tends to -1 plus 2i. Z -1 plus 2i. What is f of z? You substitute z minus 3 by z square plus 2z plus 5. That is equal to limit z tends to -1 plus 2i. Z -1 plus 2a. Already we have the roots of the denominator. So let me split into two parts. What is the first root? -1 plus 2i. So one factor. Another factor is what? -1 minus 2i. Right? Factorization. So now these two gets cancelled. Now substitute this value. -1 plus 2i minus 3 by -1. Is it 2i or I? Yeah, 2i only. -1 plus 2i minus of minus plus 1 plus 2i. So this is -4 plus 2i by 4i. By 4i. Is it correct? Any corrections? Right. Now multiply divided by I on both sides. -4i minus 2. I square minus 1, yeah, by 4. So real part is what? -1 by 2 minus I. -1 by 2 minus I. Any corrections?
Sir, -4.
Yeah, -4. Yeah. -4. So I will get plus. Oh, what happened? Yeah. This is plus I. Okay. Only one pole lies inside. That's all. Therefore, by residue theorem, integral over C f of z dz equal to 2 pi I into sum of residues at poles lie inside C. How many poles lies inside C? Only one pole. So you write that integral. So this is what? Z minus 3 by z minus 3 by z square plus 2z plus 5 dz is nothing but 2 pi I into what is the residue I got? 1 by 2 plus I. You take inside, this is pi I minus 2 pi. So pi is common, I minus 2. Pi is common, I minus 2. Remaining 2 assignment for you. Okay. And then the next one, important one, this problem. Evaluate integral over C e power z by cos pi z dz. Cos pi z dz, where C is the circle, mod z equal to 1, where C is the circle, mod Z equal to 1. Okay. Pages are over, just wait. Now try, anyone? Try this problem. First find the singularities. First find the singularities and check which singularity lies inside. Solution. F of Z equal to e power Z by cosine pi Z. The singularities are cosine pi Z equal to 0. Cosine pi Z equal to 0. That implies Z equal to what when it is 0? Plus or minus pi by 2, plus or minus 3 pi by 2, and so on. Infinitely many singular points. Okay. Among these,
Sir, pi is given, sir. Already pi is given.
yeah, pi is given. Very good. So there is no pi. So 1 by 2, 3 by 2, like that, right? Among these, Z equal to which, what is the circle? Z equal to plus or minus 1 by 2 are the simple poles, lie inside mod Z equal to 1, correct? Remaining 3 by 2 all are lies outside. This is unit circle. So 1 by 2 minus 1 by 2, 3 by 2 all are outside, right? Are the simple poles. Therefore, residue of f of Z at 1 by 2 first. Simple pole formula you can apply. Z minus 1 by 2 into f of Z. Z minus 1 by 2 into f of Z. Can you apply? If I apply this limit Z tends to 1 by 2, Z minus 1 by 2, what is this? F of Z is what? E power Z by cosine pi Z. So this factor is not getting cancelled, Z minus pi by 2. If you apply this, you will get 0 by 0 form. If you apply this 0 by 0 form, you can apply L'Hospital rule. Okay. But R, what is the formula? I can apply simple pole formula, limit Z tends to 1 by 2. Phi of Z by psi dash Z I can apply. Do you remember? Okay. Here what is phi of Z? E power Z. What is psi of Z? Cosine pi Z. Cosine pi Z. Therefore, what is psi dash Z? Minus pi into sine pi Z. This implies limit Z tends to pi by 2, e power Z by minus pi into sine pi Z. If I apply this, what I'm getting? E power pi by 2.
So Z tends to 1 by 2.
Yeah. Z tends to 1 by 2. So this is also 1 by 2. 1 by 2 by minus pi, sine pi by 2 value 1. So e power minus 1 by 2 by pi is the first residue. Next one. The residue of f of Z at what? Minus 1 by 2. Same logic. Already I had these values. Phi of Z by psi dash Z. This is a limit Z tends
So
to
e power minus 1 by it's
e power Z by minus Z into sine pi Z. So this is e power minus 1 by 2 by minus 1 by 2 sine minus pi by 2 minus 1. Correct? Any corrections? Pi will be there now. This is pi.
so in the residue value of 1 by 2.
Just wait. This is minus pi into minus 1. So what is this value? E to the power of minus 1 by 2 by pi. Okay, these two are over. Therefore, by using residue theorem, integral over C f of Z dz is equal to 2 pi I into sum of residues at poles lies inside. At poles lies inside. What is the first one? First residue is what? E power 1 by 2 minus pi. Second residue is what? E power minus 1 by 2 by pi. This is 2 pi I. Let me take pi outside, and minus also common. Minus also common. E power 1 by 2 minus e power minus 1 by 2. Now multiply divided by 2. So minus 4i e power 1 by 2 e power minus 1 by 2 by 2. Is it correct? So minus 4i, what is this value? Sin h? Sin h 1 by 2. Minus 4i sin h 1 by 2. This is the value of the integral. What is this integral? Integral over c e power z by z into cos z dz value. Done? And next problem, evaluate integral over c tan z dz. You try this, okay? Tan z dz, where c is mod z equal to 2. Answer minus 4 pi I. And next problem, using residue theorem, all of you, evaluate integral over c sin pi z square plus cos pi z square. These are solved problems in the textbook. Z minus 1 whole square z minus 2 dz, where c is mod z equal to 3. C is mod z equal to 3. And this is also simple. This is also simple. Yeah, this problem. Evaluate integral over c z into e power 1 by z dz, where c is mod z equal to 1. Z into e power 1 by z dz, right? See, here f of z is what? Z into e power 1 by z. Done? Clearly, what is the singularity? Z equal to 0, e power 1 by z. When z equal to 0, e power infinity goes to infinity. So z equal to 0 is the singularity. And that singularity, what type of singularity it is? What type of singularity? Whenever exponential functions are there, you expand it. So I am taking expansion. 1 plus x square by 2 factorial, x cube by 3 factorial, and so on. And so on, right? So take z inside, z plus 1 by 2z plus 1 by 3 factorial z square, and so on. This is what f of z is the Lorentz series expansion. Is the Lorentz series expansion about what point? About z equal to 0. Clearly, in the denominator z equal to 0, negative powers are there. And since negative powers are in infinite, negative powers are in infinite in Lorentz series expansion, what is the singularity? Lorentz series expansion, z equal to 0 is what singularity? Essential singularity. Z equal to 0 is essential singularity. Okay. And what is the residue? And residue of f of z at 0 is nothing but coefficient of 1 by z. So what is that 1 by z coefficient? 1 by 2. 1 by 2. This is 1 by 2. Hence, by residue theorem. Hence, by residue theorem, integral over c z into e power 1 by z dz is equal to 2 pi I into only one residue is there. So answer is what? Pi I. Answer is what? Pi I. Okay. A similar problem. Sine 1 by z. sine 1 by z dz, where c is mod z equal to 1. And the answer is pi I. No, 2 pi I. Answer is 2 pi I. Done. Next one. All these are evaluations. 1 by z power 4 plus 1 dz, where c is mod z minus 1 equal to 1. Mod z minus 1 equal to 1. Okay. This is important. Answer is minus pi I by root 2. Hint I am giving for this problem. Hint. Singular points are z power 4 plus 1 equal to 0. Done. So z equal to minus 1 whole power 1 by 4. What are the roots? Anyone? Yes? Cube roots of unity, nth roots of unity you can find. What are the roots? Yes? Nagakshita?
Yes, sir. Call.
In intermediate is there na? Minus 1 whole power minus 1 by 4. You have to get 4 roots compulsory.
Yes.
1 plus I by root 2. Next one, 1 minus I by root 2. Minus 1 minus I by root 2. Minus 1 plus I by root 2. These are the roots. Are they simple poles? Are they simple poles? And which pole lies inside? You have to decide. Which pole lies inside? You have to decide. What is the C is given as? What is the C is given as? Mod z minus 1 equal to 1. You substitute in this. Okay. At z equal to 1 plus I by root 2. Or you can draw the graph also. Doesn't matter. Mod z minus 1 equal to 1 plus I by root 2 minus 1. 1 plus I by root 2 minus 1. What is this value? 1 by root 2 minus 1. What is this value? 1 by root 2 minus 1 plus I mod. So what is this value? Square root. 1 by root 2 minus 1 whole square plus 1 square root. Done. You expand this and find which pole lies inside. Which pole lies inside. I think this is less than 1 maybe. Definitely. 1 by 2 plus 1 minus 2ab minus root 2 plus 1. So what is this value? 2 plus 1 by 2. 3 by 2 minus 1.414. This is more than 1, huh? Yes? Or you can write like this.
So there's one more one.
Huh? Square root is there, na? So it is less than 1. Therefore, z equal to 1 plus I by root 2 lies inside C. Similarly, you find others. And find the residue. All are simple poles. Okay. This is one problem.
Sir, it's greater than 1, sir.
Which one?
It is
You
5 by
left
2.
one more 1, sir.
1 by 2 plus 2.
Wait. 1 plus I by root 2 now. If I draw the graph, center is this one, right? So this will be what? This is 0. 1 by root 2. Where is 1 by root 2? Here 1 by root 2 is there. And I by root 2. Where is I by root 2? It must be somewhere here, right? Why I am getting this? Just check once again. 1 plus I by root 2 minus 1. 1 by root 2 minus 1 plus I, correct? Oh, this is I by root 2. All of you. This is I by root 2. There's a mistake. So this will be 1 by 2. This will be 1 by 2. 1 by 2, 1 by 2, this is 2. Correct? 1 by 2, 1 by 2, 1 plus 1, 2. 2 minus root 2. 2 minus 1 point means what?
Less than only.
Less than 1 only? Yeah,
Yes, sir,
now
less
this
than
is
1.
less than 1. Now this is okay. Okay, some mistakes. You try this problem and apply residue theorem. Don't forget. Integral over C z plus 1 into cot z by 2 dz. C is mod z equal to 1. C is mod z equal to 1. Okay. What are the pole? Anybody? Hint I am giving for every problem. Hint. F of z equal to z plus 1 into cot z by 2. Z plus 1 into cosine z by 2 by sine z by 2. So what is the singularity? Singularity is z equal to what? 0. And is simple pole. And is simple pole lie inside C. Right? Inside C. You find residue. That's all. Only one residue is there. Answer 4 pi I. Just wait. Evaluate. Yeah, you can do all this. Right. E power minus z by z square dz. C is mod z equal to 1. C is mod z equal to 1. That problem is over. Next. Integral over C. E power 2z by z plus 1 whole power 4 dz. C is mod z equal to 2. Mod z equal to 2. And next one, z into secant z by 1 minus z whole square dz. C is mod z equal to 3. C is mod z equal to 3. Okay. And okay, I will stop here. These are the assignment problems. Solve them. Okay. If any doubts, you can raise it. You can ask in the next class. Tomorrow, what time you are free?
Tomorrow